Hello Legacy students, Marsh here. So today we're going to talk about E. Now, E is a really awesome letter, and he's a really cool letter that we relate to a lot in math. What you're going to want on you, your notes, calculator, you're going to definitely want like a scientific kind to find him, find E, pen or pencil, and then you're going to need some graph paper. You're actually going to need 3 things of graph paper, not just 2 today. So, remember, you start talking about pi, probably in geometry, maybe even earlier, and what does it represent? Well, pi was, remember, the quotient between the circumference and your diameter. So we were able to find that it was related. It related a lot in circles. And we could simplify expressions containing pi, something like this. So 5 pi squared, that would have been 25 pi squared, right? Because you gave the pi squared in, just using our exponent rules. Pi to the -1 would move you to the top, right? Because you have negative exponents, it's going to flip around on your fraction. I'll simplify the 15 over the 20, and I would get 3 over 4, and then be pi to the 6th. Right? Because the pi to the -1 would move up, become positive, so I'd get pi to the 6th. So now, guys, what we're going to talk about is what's known as Euler's number. And that's how you pronounce it. Kind of sounds like Euler's number. Now, Euler's number is approximately 2.71828. It's another really important number that happens in real-life situations quite a bit. And it's one of the numbers just along with like I and the pi. But E is what we're focusing on today. Now, you're probably saying, well, where'd this Euler dude get this number? Well, here's what he found out. That exponential growth formula that we looked at, the compound interest formula, well, what Euler started to do was kind of look at, well, what if we compound for each month? What if we compound for a year, hour? What about each minute? Well, what he started to realize is as he created those formulas and started computing the information, it got really strangely close. So I put my answers here for each of these. It started to get really close to Euler's number, or E, 2.718. And he went, that's kind of interesting. As I start to compound continuously, or as I basically just never stop compounding, I reach a, if you want to consider it a plateau of growth of 2.718. So he realized that that would be the growth amount. Thus, Euler's number was born. So, what we're going to want to focus on today is how do you simplify stuff with E, and also how do we graph things with E. So, first parts, let's simplify expressions. You're going to want to remember those exponent rules from long ago. So you're going to want to bring those up in the old noggin. Find those in there. Alright, so if you remember, guys, what you did when you had 2 of the same base multiplied, which is basically E, you added the exponents, right? So first things first, let's multiply the coefficients. So 2 times 6, that is 12. And then I'll have e to the -3 times e to the 5th. Well, I'm going to add the exponents. So it's going to be 5 minus 3, right? Or 5 plus a -3 if you want to consider it that. So it'd be 12e to the 2nd. Now, what is that approximately? Well, 12e to the 2nd, guys, is approximately 12 times 2.712 approximately to the 2nd. So it actually is 88.67. That is actually what the decimal approximation is that. Now, there is an E button on your scientific calculator, and if you need help finding him, usually he is the second key to the LN button. It says LN on it. It's right below log as well. So look for it. If you need help, I will help you find it when we get into class. So now I have 24e to the 8th divided by 4e to the 5th. So very first thing, let's divide the numbers. 24 divided by 4. Well, that's just 6, right? And then I need e to the 8th divided by e to the 5th. Now, if you remember, guys, what we did is we subtracted exponents when they were divided. So this would be e to the 8 minus 5, which is the same thing as 6e to the 3rd. Now, I did that quickly on my calculator, and I got 120.51. Okay, something to keep in mind just to kind of get a good guesstimate of what that actually means. Let's also find what this one is. So I got 4e to the 2x to the 3rd power. So remember, guys, when you had an exponent outside parentheses, we basically distributed, for lack of a better term, distributed it in. So we had 4 to the 3rd and e to the 2x times 3, right? So ultimately, 4 to the 3rd is 64, and e to the 6x. Now, what else can we do with e? We can graph him. Yay! Graph e. Alright, so let's graph f of x equals e to the x. So, parent graph. This is the parent. Some key points you're going to want to know about e to the x. If I plug in 0, I am going to get 1, because remember, any base to 0 is going to be equal to 1. If I plug in 1, we're going to get about 2.71, which is what e is actually stood for, right? So those are going to be some key points that are going to be on our graph. And it does, notice, guys, as let's say if we plug in a negative value, because that would be e to the negative 1, you're going to get something that's very close to 0, because that would be 1 over e, which should basically be 1 divided by 2.7, if you want to consider it that. So e does, in fact, since it is an exponential graph, just like our growth and decay, he is also going to have an asymptote, just like the other ones. Now, this guy is a growth graph, because look from here, guys, it looks like it's climbing upwards from left to right. Your asymptote will be y equals 0, so it is right here. It's never going to touch it. It's not going to cross it. It's just going to kind of slowly and slowly get closer and closer. Okay? My domain, I am going to cover all the real numbers, so negative infinity to positive infinity. And my range, notice, guys, I'm not covering 0, but I am going up to infinity. So thus I will have parentheses on both sides. Now, let's look at exponentials with a little bit of a change to them, a little bit of transformations. So remember, guys, my parent graph is still going to have the points 0, 1, and 1.27, because all of my parent graphs are going to be y equals e to the x on every single one of these. So let's graph those in my red color. So it's going to be 0, 1, and 1, 2.7. And remember, guys, you just kind of do something like this, and it's going to growth up right there, all right? Now, translated graph. So this is 3 times e to the x plus 3. So the very first thing we need to do is this vertical stretch of 3. So I'm going to put that in actually blue here, and then we'll move those dots left 3. So, very first thing, if I take this times a vertical stretch of 3, my 0, 1 is now going to be 0, 3, right? Because if I plug in a 0 into this function right here, I'm going to get times 3. 1 times 3, right? So 0, 3 is going to be a dot on here. And then I would have not 1, 2.7, but whatever 1 times, or whatever 2.7 times 3 is ultimately, which is a little bit above 8, right? Because 2.7 times 3, that would be about, yeah, it's a little bit above 8. So 1 and then just above 8, about right there. So that would be my just 3, so my blue is just y equals 3 times e to the x. Now I need to do this plus 3 up there, which is left 3. So I'm going to change my color here into purple, and now my blue dots are going to move left 3 to get my final graph. So 1, 2, 3. 1, 2, 3. Now notice, guys, I did not move up or down on this graph. Thus, my asymptote will still be at 0. It's just growing much faster this time. Okay, now this is a growth graph because it is looking like it's a climb. My asymptote, as I was saying, is still y equals 0. We didn't move up or down, so thus my asymptote has not changed. My domain, still same thing. Whoops. Negative infinity to positive infinity. And my range is still 0 to infinity because we have not moved up nor have we moved down. Now let's take a look at another kind of graph. F of x equals e to the negative x plus 1. Now guys are probably stopping and saying, Marsh, we've never had a negative x in an exponent. Hold with me, I'll talk about that. So first of all, we got our parent graph. Key points again, 0, 1, and 1, 2.7. So 0, 1, 1, and 2.7. So my graph, guys, is going to do something like this. Remember, your parent function is always going to look something like that. Now, I got to do some flipping and some turning. Now, here's where that negative x is going to come in. Now, remember, guys, let's just do a sidebar over here. If I had negative e to the x, I flipped it about my x-axis, so we're mirrored over the x. If you have a negative on the y-axis, or in the exponent, that is going to reflect you over the y-axis. So I'm going to change color here. We're going to go to green, I think. I'll make this green. So what I'm going to do is take these dots and reflect them over the y. Now, since he's on the y, there is no worries. He's just going to stay on the y. This guy, though, he's got to flip over here and flip over there. Now, I need to do that up one bit. So let's go ahead and change color again. I changed to orange. So I'm going to go up one with this dot and up one with this dot. There we go. Now, guys, if you remember, just like when we did our growth and decay, when I moved up, that changed my asymptote. So now my asymptote is going to be at y equals 1, because that is how we moved up. So then if I connect my dots here, my orange ones, there we go. A little hard to see, but that's okay. Now notice, guys, this is a decay graph because it does look like a slide. Here's a good way to be able to think about. If you have a negative exponent here, okay, that is how you know you have a decay graph. If my exponent is positive on the e, that's going to cause you a growth graph. Something to keep in mind, maybe a little note to write to yourself. Negative exponent equal decay, positive exponent equal growth. Okay? Domain, guys, it's still negative infinity to positive infinity. And my range is not from 0 to infinity because I did move up one. So it's actually going to be from 1 to positive infinity. And that's the end of this video. See you later, Sabers.